Hello and welcome to I Can Science That. Just earlier today, I had a little discussion live, and I'll link it up there for you guys if you want to watch it. So I was talking to someone from YouTube called I Thunk About, and the discussion topic was Peakfinder. The question that we started with was, is Peakfinder a globe simulation or a flat simulation? And right off the bat, I emphasized that Peakfinder is a simulation. This is not reality. We're just going to look at this one app, this available app, to see what does it show us. And I want to be very clear that I'm distinguishing that from what the real world is, what we see in photos. We're not talking about that. We're just talking about Peakfinder. So the interesting thing about that to me was that we had this conversation and we weren't really able to resolve it. So I thought I'd put my thoughts down and ask I Thunk About maybe to go over my thoughts point by point and stop me where I'm wrong, where you disagree. What I want to do is just get to the root of just this one question to show that we can. I have this hope that we can. So let's look at Peakfinder. This is the web version. Let's check it out. Okay, and we're going to be trying to address the question. Here's the question I'm trying to answer. Is Peakfinder a globe or flat simulation? That's the one question I want to try to answer with this. And here is the various evidence that I would use to try to answer that question. See, if Peakfinder is a globe simulation, then I expect that mountains in the distance will be hidden as they go into the distance. They'll be hidden from the bottom up. That would be a globe feature. If it was a flat simulation, then we would not see that. We would not want to see the bottoms of things cut off. That would mean it was flat. See, if it was flat, then we could see all the way to the bottom of the mountain, or we'll be looking at an island in this example. So if we can see all the way to the shoreline of an island at any distance, that's an indicator that it's flat. If the bottom of the island is cut off, that's an indicator that it's a globe simulation. Okay, and we can get a little bit more specific. We can ask how much of that bottom is being cut off. We'll use curve calculators to see what the globe predicts the bottom amount should be cut off. Okay, and then, but how about the flat? See, this is the thing. This is where we get into a real sticking point. I insist that in order to be fair, we have to apply the same exact rules to both. If there's a rule that the globe must follow, we have to have a matching rule for the flat option, right? For example, if we have this rule that the bottom is cut off for globe, we also have a rule that for flat, the opposite must be true, right? Right? Okay, so for the curve calculator, that'll be our rule for the globe. And for the flat side, what is the matching curve calculator? Well, that would be 0. There shouldn't be any curve, right? If the curve is not there, then that equivalent calculator should give us 0. So if we're going to compare Peakfinder to the curve calculator for globe, we should compare Peakfinder to no curve for flat, right? And we'll see which one does a better job. Okay, and here's another thing I threw in there towards the end is eye level. On a flat simulation, it's often said then that the horizon always rises to eye level. Okay, horizon always rises to eye level. We've heard that before. That's a flat feature. Whereas if it's a globe, we have to have the matching demand that the horizon must drop below eye level. So if we see things dropping below horizontal, that's a globe feature. If they do not, that's a flat feature. Okay, and then lastly, seeing more. We're going to be looking at islands. So if I raise the altitude and look down, am I able to see more of the shoreline? Is the front, and I'm not talking about seeing over hills. I'm talking about seeing in front of the island. If there's part that was cut off by the ocean, going up in altitude should reveal more only if it is a globe. If it is a flat simulation, then going up higher in altitude does not reveal the front of it. Okay, the immediate pushback I anticipate is disagreement with these rules. For some reason, these rules, that's okay. We agree that all these must be true. But when I put these opposing rules, applying the exact same rules just to a flat surface, no. Wait, that's not fair. If we're going to give these rules, we have to accept the rules for the other side as well. The pushback I expect is that all of these things assume no atmosphere. They assume nothing obstructing, no haze, no difficulty in seeing all the way to the tiny details of the beach and so forth. And yes, that is correct. We're positing here that all of these things did not have any atmosphere involved in the calculations. So if we're not going to apply any atmosphere to this side, we are not allowed to apply any atmosphere to this side. Okay? And if that bothers you, then let's go ahead and apply atmosphere. So if we're going to apply some atmospheric rules over here, we must also apply the same exact atmospheric rule here. Right? In order to be fair, we have to apply the rules the same. So, whatever atmosphere you wish to invoke, we must apply evenly to everybody to be fair. Here we go. Here's the same location that we did in the stream, and I've got it on screen there for you. These are the latitude and longitude, and here it is converted to decimal in case that's easier. We'll be looking at 132 degrees heading and use Peakfinder, zoom all the way in. Okay, there you go. I've punched these numbers into Peakfinder, and you can see that's where the decimal conversion is right there. Let's look over to 132 degrees. We'll find Mauna Loa. Oh, I'm set to meters, so let's get into feet mode. Feet. And zoom all the way in. There it is. Okay. This is what we should see in the screenshot. I also have the grid turned on. That was something that that Thunkabout liked, to see the grid. So we could see there is 130 degrees right there. Okay, what are we going to do now? The first question was, is this mountain that we're looking at, Mauna Loa, which is part of the big island of Hawaii, is that being blocked by the curve of the Earth? Where is the curve in this image? If Peakfinder is a simulation of a globe, then this line, this black line here, must represent the ocean, and part of the big island would be back here behind the ocean blocked. How do we determine that? Easiest way to determine that is just click on the mountain here and see what altitude do you see. Here I am, I'm seeing 12,000, I can get it down to 12,642 feet. Why can I not go below that? If this line is 12,600 feet, there's 12,000 feet of island below there. This island has been cut off from the bottom. Has the island been hidden by a curve? We took a look, we zoomed in, and we saw in this little shot here, we see that 12,753 feet is hidden. Okay, So let's look at our little chart. How did we do on our first test? The bottom of the island was hidden by something. So that indicates that's our first test that says that Peakfinder is a globe. It's passing the globe tests. It is failing the flat tests. Okay, and the immediate response is going to be, but we see too far. This 12,700 feet, that is wrong. That is incorrect. So we're going to go to this curve calculator, and I've just got a screenshot. Let's just go straight to the screenshot here. Go into this curve calculator. There's a link for it, and punch in the height that Peakfinder has for that location is 565 feet, and the distance it's showing us is 183 miles. And according to this curve calculator, 15,787 feet should be hidden. However, Peakfinder is showing us that we're seeing all the way down to 12,750 feet. So we are seeing well below the amount that should have been cut off. What should have been cut off was 15,000 feet. That's taller than Mauna Loa even is. The entirety of Mauna Loa, according to the curve calculator, the entirety of the island should be below the curve. But Peakfinder says we can see the top 1,000 feet. Just 1,000 feet, the top 1,000 feet of the island is visible. What's up with that? By this standard, we see certainly too low. As often said, we see too far. We're seeing stuff that should be behind the curve. Agreed, 100% agreed. If we're going to be objective, that's what this says, okay? The Earth curve calculator says we should be 15,000 cut off, but we're seeing 12,000. Okay, let's put that in our little chart. We predicted using the Earth curve calculator that this much would be cut off. Peakfinder says, no, only this much was cut off. So we subtract and we find Peakfinder disagrees with that Earth curve calculator by 3,000 feet. Peakfinder is showing us 3,000 feet too much. That's pretty bad, right? That's pretty far off. Wow, that's a major fail, right? It's a major fail for this globe hypothesis. But I want to remind you now, every rule we apply to our globe test, we must apply equally to the opposing point of view. How do we do on a flat test? What is the predicted amount of hidden distance on a flat, zero refraction, no atmosphere? What is that? Well, that is 0. Flat predicts 0, but Peakfinder showed 12,700. So the error for flat is 12,753 feet, compared to the error that we were appalled by this 3,000 feet of error that the globe generated. But are we just going to accept the 12,000 feet that the flat is wrong? I don't think so. I mean, if we just take this is our only criteria that we're going to test by, we're going to have to say globe didn't do very well, but it did better than flat. So that's another win for the globe, right? That's another win. 3,000 is significantly less than 12,000. Any reasonable response would say, but no, that's not fair. This 0 stuff, this is not fair. We should have some obstruction due to the atmosphere. Okay, fair enough. If we're going to apply some kind of atmospheric obstruction, though, on this side, we have to also apply the atmospheric obstruction on this side. That's just fair is fair, right? Fair is fair. So Look at the Earth curve calculator. This is right off the website that we just used for the Earth curve calculator we were just using. It says right on there, light travels in straight lines, meaning no atmosphere was used in this calculation. This calculation here that we have used for this table has no refraction. So this is the no refraction, no refraction. If we want to look at what refraction does, we can do that. Whatever atmosphere you want to invoke for your side, we're going to want for our side too. It's just fair, right? If you get it, we all get it. Okay. How are we going to apply atmosphere? Well, it turns out that's actually studied and known. Here's a link for Walter Bisland's Earth Curve Calculator, the Advanced Earth Curve Calculator. And you'll see in here, there's a refraction option built in. Let's go and check it out. This is the website for Walter Bisland's Earth Curve Calculator, the Advanced Earth Curve Calculator. Lots and lots of options on here. Yes, it is more complicated than the little box where we just put in two fields. But this one's going to allow us to explore this difference. Okay. First off, I want to put it into miles and feet. Our observer was 565 feet, looking at a distance 183 miles away. And I want for refraction, well, let's start with zero. Zero refraction. This is the hidden amount, and it's very, very similar to what we saw before, 15,800. Let's apply an atmosphere. Click this button right here, standard atmosphere, a standard atmosphere, and now look at the hidden amount, 12,662 feet. Okay, so we went into Walter Bisland's Earth Curve Calculator, and we're going to punch standard refraction. That's that button right there. And it's going to show us 12,662 feet of hidden. So let's go back to our little chart. Remember our little chart? And let's fill in the correct prediction right there. So that is 12,662. Remember, Peakfinder gave us 12,753. So the error we got out of Peakfinder now is down to 91 feet. 91 feet. And remember that last little pixel you can't quite click on? Apparently, that little last pixel is 91 feet tall. So now, to be fair, we should be able to somehow fill in a prediction here for how much of the bottom of the Big Island of Hawaii is obstructed by the atmosphere as a result of, flat Earth calculations. Honestly, I don't have anything for you. I don't really know. I don't know how to apply that. There's no known formula for that. If you have one, great. If your formula can generate 12,000 feet, the bottom 12,000 feet of a 13,000 tall peak was obstructed by the atmosphere, then show me that. We'll talk about it. We'll put it in here. This is the best we can really estimate here for the globe. This is what the globe model actually says. Now, at this point, a lot of people are going to complain, but that's not what the globe says. You added something. There's a fudge factor. No, this fudge factor that we added, the refraction, is the standard scientific model of the atmosphere. Now, the atmosphere, obviously, it varies. So it varies with weather conditions from day to day, time to time. So you can't know exactly what you're going to get. So we have a standard atmosphere. If you just take the standard atmosphere, which is sort of like an average or normal kind of atmosphere, that's the amount of refraction that you get with a standard atmosphere. And, there you go. It is an estimate, right? It's an estimate. And the estimate, as you can see, very closely matches what Peakfinder showed us, right? So that's a big clue that whatever calculations Walter Bislin is doing are very similar to the calculations that Peakfinder is doing. Remember now, before anybody gets upset, we're only evaluating Peakfinder. This isn't reality, this isn't photographs, this is just Peakfinder. Peakfinder matches Walter Bislin's calculator very closely. So that's a strong clue that they're probably using the same calculations, as that is a standard scientific practice to do. I think that's a good bet. That's exactly what's happening. Okay. Next question was, what about eye level? Okay, let's take a look at eye level. Let me click, try to hit pretty much the top of the mountain right there. Okay, that's as high up on the mountain as I can really get with my little pointer. And you can see it is indicating 13,563 feet, just shy of the known peak. And this little number right here is showing negative 0.3 degrees. Okay, I got my little insert here. Negative 0.3 degrees. What does that mean? That means, according to Peakfinder, not real, it's not real, it's a simulation. According to the simulation, you must look down from eye level by 0.3 degrees in order to see the top of Mauna Loa from this observer position. The very, very peak, the top of Mauna Loa, is 0.3 degrees below eye level, according to Peakfinder. Now, let me remind you, the top of Mauna Loa, indicated here on my screenshot, the point I'm looking at least, is 13,560 feet. And the observer, I'll remind you, it's right here at the bottom, is at 565 feet. So we're looking up 13,000 feet. At what distance do you have to go for that, looking up 13,000 feet, to be negative 0.3 degrees? If this is a flat simulation, that will never, ever happen. There is nothing that can make a 13,000 foot gain become down without invoking some kind of curve. Right? This simulation includes a curve, and there it is right there for everyone to see. Let's look at our little chart. We already have hidden by the curve. We have hidden amount. Let's look at eye level. Yep, it does drop below horizontal. It clearly does. You see the negative number there. The horizon does not rise to eye level in this simulation. So this simulation, once again, by our third test, is not a flat simulation. This is a globe simulation. Okay, this leaves our last test, islands. Do you see more of the island as you go up in altitude? Let's check it out. Here we are. You can just hit this little button right there to raise your altitude. Let me make that go away. I'm at 565 feet right now, and that's ground level at that location, according to Peakfinder. If I just go up a little bit, boop, 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 see how we're revealing more of the island as I just go up? It's not bringing the island closer to me. Why is the island getting bigger? What? Why am I seeing stuff that was below the water? So all this was below the water. This was below the water. Over here at 130 degrees. Let's go up a little higher. There we go. We're past 130 degrees. We're past 133.5. If I go back down to ground level, those are way below the ocean. That's below the ocean. But as I go up, I see more and more and more and more of the island is pulling up from below this water line that's being drawn here in the simulation. Here I've got a little screenshot where I've raised my view up 1,008 feet There we go. We're at the original 565 plus 1,008 feet. Got a little screenshot here of it. And look how we can see more now than we could before. Let's see, this is it before. This is at 565. Let's go up 1,000 feet and we see more. We see this little piece here. This little thing was completely under the horizon before, but now we've revealed it. This peak over here wasn't visible, but now it is, right? So going up clearly is revealing more of the island. That is our fourth test. So we have once again passed the globe simulation test and failed the flat simulation test. All right, summarize. First off, I'm going to repeat it again. Peakfinder is just a simulation. It is not reality. I'm not claiming that it's reality. I'm not judging it against reality. In this video, I'm not even entertaining at all any discussion of how close Peakfinder matches reality. If you find yourself insisting right now and screaming at me that that's not fair, that Peakfinder is not reality, and there's photographs, but I have photographs, that's not the question. The question is, what is Peakfinder a simulation of? Not what do your photographs show, okay? All right, Peakfinder, I have concluded Peakfinder is a globe simulation. We tested it in 4 different ways. It passed the globe test in all 4 ways. It failed the flat test in all 4 ways. Okay, and we have also shown Peakfinder uses standard refraction. So if you use that Earth curve calculator or your back of the envelope calculators that just don't include any refraction, you're going to find that Peakfinder shows you more than that. You can see farther in Peakfinder than you could in a purely geometric simulation. Okay? And that is because that's what refraction does. Standard refraction. Standard refraction is standard part of globe science. Okay? And last, I really want to emphasize this. We have to apply the same rules evenly, right? If your rules are going to insist that there be a geometric horizon that has no refraction, then you must apply that same geometric horizon with no refraction to the flat side. If you say, I see too far for this globe simulation, you must ask, do I see as far as the flat would show me, right? We have to apply that same rule of comparison of how far we see versus how far we predicted. We have to compare that and apply that evenly. That's all I'm asking for. Apply that evenly. And what would really help, I think, is as you do things like this, as you do these judgments, write the rule down. Maybe write down what is the rule that you're applying, and then show us all how you're applying it on both sides. All right, y'all. So Peakfinder, it's pretty cool. It is a globe simulation, though. Maybe in another time we can come back and talk about what reality looks like. But Peakfinder itself is absolutely a globe simulation.